Hello, students. We are here to discuss conservation of energy laboratory. This is an introduction to the lab on conservation of energy. Remember, in the lecture, we learned that the total amount of energy in a system never changes. That's the principle of conservation of energy. We just learned that the total amount of energy in a system never changes. Never changes. That's what we learned in the lecture, meaning that energy cannot be created or destroyed. Energy cannot be created nor destroyed. You cannot create or destroy energy. But energy can transform from one form to another. Energy can transform from one form into another. All right, let's look at our experimental setup. Experimental setup. Our experimental setup is as follows. We are going to have an air track. Let me see if I can pull two diagrams one. The air track here. Like that. Okay. Right there. Okay. There, and then position 2 of the air track will be here. Okay. All right. Okay, it's kind of hard here to draw, but that's position 1 and position 2. Okay, in position 1, we have the pulley is right here. Let me see, that's the table. Okay. Okay, so let's do this. Let's move this a little bit. It's a table to here. And let's move this a little bit to here. Okay, good. And then we are going to have our pulley right here. Okay, this pulley here, the pulley here. And oh, it looks like it has to be a little bit up. Sorry, it's a bit bigger. Okay, and then I have my car right here. And there's a thread that moves through here. It's a thread here. And there is a car here. Oh, there's a hanger here, mass M. And there's a bigger mass here. Now, once the car has fallen down, it will fall through the height H. I mean the hanger. Once we allow it to fall down, it will fall through a height H. And then at that time, I will see my hanger still moving somewhere, maybe here. Okay, so this will be the initial position of the mass. Then it will fall down all the way to the ground, all the way to the ground. Okay, so this is where the mass will be upon falling, and this is where the bigger mass will be upon falling. So let's be careful here. Now, we have to realize that there is a potential energy loss when the small mass moves down here. There is a potential energy that will be lost. Realize that the bigger mass is not changing its height, so the potential energy remains the same. No change in potential energy for the bigger mass because it maintains the same height, same level. But for the smaller mass, there is a loss of potential energy equal to mg times the height. So that will be the potential energy lost by the smaller mass. Now, that energy has to be accounted for. It has to be accounted for. If we ignore friction on the surface, by the way, we are using, air track. So there's an air cushion on the surface here, air cushion, or we consider it frictionless. And we can ignore air resistance as the mass is falling for our experiment. So what are we saying? That this mgh has to be accounted for. The loss in potential energy has to be equal to what? It has to be equal to the kinetic energy gain. So there has to be equal to kinetic energy gain. The kinetic energy gain has to be equal to 1/2 times the total mass that is falling. We have the smaller mass that's falling and the bigger mass. So two masses are moving actually. So there will be two masses here. I don't have enough space there. So times v squared. The v squared is the striking velocity here. Now let me write this again because I don't have enough space. So I'm saying that this is a demarcation here. I'm saying that the kinetic energy gain must be equal to 1/2 times the total mass that's moving, and then velocity squared. This velocity here is a striking velocity, or velocity just before the mass hits the ground, v. All right. So if all things are okay, no friction, no air resistance, then for sure, this loss in potential energy must be equal to this gain in kinetic energy. Yep, because energy cannot be created or destroyed. Energy has to be the same. So we are expecting that the mgh must be equal to 1/2 total mass here times v squared. Now, we are going to be troubled a little bit in terms of measuring the v. I would like to explain how to measure this v here. It is challenging in this experiment to measure v because it is a striking velocity. The velocity of this mass just before it hits the ground. Now, let me explain. What we need is that this mass, once it hits the ground, this car here will be moving at a constant velocity because at that point, it's no longer pulled by the rope anymore. You know, throughout here, as the mass is falling, there is actually a net force acting on the system of masses. That net force will cause the system to accelerate. So the bigger mass m here will actually be accelerating as the mass is falling. But once the mass hits the floor here, there's no more tension here. Tension will be zero at that point. And therefore, the mass here will be moving at constant velocity, constant speed. And that constant speed is what is actually equal to the striking velocity here. So we have to design or set up the experiment so that we are able to measure the constant speed of the mass here once the small mass has hit the ground. So I don't have enough space here, but this is the position to set up your gate. There'll be a gate here, another gate here. The space is too small, but that's where to set up your gate. There'll be two gates here, one gate here, another gate here, and then these gates are connected to a timer, right? So we want to measure the constant speed. So set up the gates immediately after the mass has hit the ground. So put the gate right there, another gate here, and you can measure your constant speed moving through there. So the speed will be given by distance between the two gates. This is the distance between the two gates, distance. And then you divide by time taken for the car to pass through the gates. Of course, we need more space here. This is just a diagram. More space so you can grab the car. More space. So we need more space there so the car passes through the gates and then you can grab the car somewhere there. You need more space. Maybe let me try to redraw this situation so you understand what I'm trying to say. So we need to make sure that the car has to be somewhere here. Actually, maybe somewhere here, bigger mass. And then at that point, we should allow the car to pass through two photo gates. Enough space here. So at this point, the rope is not actually, there's no tension actually. There's no tension because it has already touched the ground. The mass is right here. There's no tension. So the mass will be moving at a constant speed. This is the distance I was talking about. This is the distance. And the timer will be connected here. There'll be a timer here. Timer. All right. So the velocity will be the distance divided by the time. And that will be the striking velocity at the surface here. It will be the same. All right. So we're going to set up the experiment so that we give the mass here a chance to go through the photo gates whilst moving at a constant speed, and that will be the striking velocity. All right. So that's the logistics. But let's think about the data analysis. Let's think about how to deal with the results. Well, you're going to have to compare mgh versus 1/2 m plus capital M and then v squared. So you're comparing the loss and the gain. So that's the loss of energy and that's the gain. Now, you need to calculate percentage error. You need to compare the mgh and 1/2 m plus mv squared. So you're going to talk about percentage difference. You will calculate percentage difference to see how close the loss in potential energy is equal to the gain in kinetic energy. So percentage difference will be calculated as the absolute difference of potential energy loss minus kinetic energy gain. All right, so this is the loss in potential energy. This is the gain in kinetic energy. Okay, potential energy loss, kinetic energy gain. Then you divide by the average of the two. So the average will be 1/2 potential energy loss plus kinetic energy gain. Then you multiply by 100%. So the result here will be percentage difference. If potential energy loss is close to kinetic energy gain, we are hoping to get a smaller percentage difference. A percentage difference of about 10 or less is good. It means that Indeed, the potential energy loss is equal to kinetic energy gain. There might be small differences due to a number of things, and that's where you talk about sources of error. It could be energy transformations into other forms of energy. If you look at the experimental setup here, you realize that we assume that the surface is frictionless. We use an air track, of course, but we may not have a perfect environment. We also assume that no energy is lost through the rotation of the pulley here. The rotation is the pulley is spinning, and some of the energy is actually taken by that. We also ignore the effect of air resistance on these moving masses, this one as well as this. Air resistance can be an issue as well. Think about the measurement. We said that it is very, very tricky to measure the striking velocity, to measure the speed, to measure the speed of the, it is very, very tricky to measure the speed of the mass just before it strikes the ground. The striking velocity is very, very difficult there. You have to design your experiment carefully. So if you do not design your experimental carefully, you might end up with experimental procedural issues. There's a measurement issues, there's a system issues, device issues, all those things you have to think about and see how they can contribute to the percentage difference or contribute to the error. All right, so that's it. I'll stop here. I hope you are going to complete this lab without any difficulties. In the data table, I tried to complete row number 1. Row number 1 is completed for you, so you have an idea of how the numbers should look like. So row number 1 of the data table has been completed for you. Please complete the rest and let me know if there is any other question. All right, bye for now.